Welcome to this explainer. So, you're walking down the street, looking at your map, and suddenly, your little blue dot just jumps across 3 city blocks. Or maybe you're flying a drone, and it just randomly veers off. We've all been there. It's super confusing, it's annoying, but honestly, it's also a deeply fascinating quirk of modern navigation.
You really have to wonder, why does your location suddenly jump like that? Today, we're putting on our detective hats to track down the technical villain behind this mystery. We're going to dig right into the data and the physics to see exactly what is happening to those incredibly delicate signals traveling 20,000 kilometers from space right down into the palm of your hand.
Okay, let's kick things off with Section 1. What is multipath? Let's meet our prime suspect.
As our source material lays out, multipath happens when a GNSS signal takes, well, more than one route to reach your device. It's kind of like, imagine shouting in a massive canyon. The sound bounces off the rock walls, right? And your ears get completely confused about where the shout actually came from because you're hearing all these overlapping echoes. Well, your GNSS receiver experiences that exact same sensory confusion just with invisible radio waves instead of sound.
Looking at this comparison, you can really see the contrast. On one hand, you have the direct path, straight from the satellite down to your antenna. That's our hero, getting the big green checkmark. But then you have the reflected path. This trickster signal bounces off buildings, water, or the ground, taking a massive detour before it finally hits your receiver. Because of those bounces, your device ends up catching multiple, slightly delayed versions of the exact same signal. What a mess, right?
Which brings us to Section 2, the timing problem. Let's look at how this actually tricks the math inside your device.
You see, GNSS positioning is entirely about timing. Your receiver uses 3 pretty simple logical steps to find you. Step 1, it records how long the signal took to travel from space. Step 2, it multiplies that travel time by the speed of light. And step 3, boom, it calculates the distance. But here's the kicker. Those bouncing, delayed reflections we just talked about, they completely sabotage step 1.
Because that reflected signal took a detour, it arrives a tiny fraction of a second late. And since your receiver multiplies that time by the speed of light, which is obviously incredibly fast, even a microscopic delay is a huge deal. The math is unrelenting here. The receiver literally calculates that the satellite is farther away than it actually is. That false distance calculation directly translates to that super annoying position error on your screen.
So, moving on to Section 3, real-world impacts. Let's see what these invisible mathematical errors actually look like when you're out in the field. Now, normally you might just see an error of a couple of meters, but the severe symptoms, the crazy jumping, those weird oscillations, and actual persistent measurement biases, those happen in specific danger zones. Think about urban canyons, walking surrounded by massive skyscrapers. Those buildings act like giant glass mirrors for radio waves. The same thing happens near large bodies of water or big metallic surfaces. Basically, if an environment looks like a pinball machine for radio signals, you're going to get some serious multipath.
And the source breaks this down into 2 distinct types of culprits. On the left, you've got code multipath. These are the blunt instruments. They affect the main pseudo-range, causing big, clunky, meter-level errors, and honestly, they're pretty tough to eliminate. Then, on the right, you have carrier phase multipath. These are subtle saboteurs. They cause tiny, centimeter-level errors. Now, a few centimeters won't ruin your walking directions, but they will absolutely wreck high-precision professional tasks, like RTK or PPP mapping, that rely on absolute pinpoint accuracy.
So how do we fix it? Let's jump into Section 4, mitigation strategies, and see how the engineers fight back.
Our best countermeasures really fall into 3 main buckets: hardware, environment, and processing. On the hardware side, engineers design specific physical tools, like choke ring antennas and carefully placed ground plans, to physically block reflections from hitting the sensor. The environment fix is, well, it's pretty simple. Just try to get out under an open sky and physically avoid walls or water. And finally, processing. This is where the real magic happens. Advanced receivers use software, multipath-resistant algorithms, and multi-frequency GNSS to literally outsmart the reflections and filter out the fake delayed signals.
If we distill everything from our source material into one single major takeaway, it's this exact quote right here. Multipath is reflected GNSS signals tricking your receiver into thinking satellites are farther away, causing positioning errors. Honestly, that is the entire phenomenon solved in one elegant, perfectly packaged sentence.
So the next time your map decides you've miraculously teleported across the street, don't just get mad at your phone. Look around at the glass, the water, and the metal surrounding you, and ask yourself, what invisible obstacles are reflecting my signal right now? Thanks for joining this explainer. Keep your eyes open to the invisible physics all around you, and as always, navigate safely.